Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Welcome back. In our last lesson, we looked at systems of supply, how electricity is generated, transmitted, and distributed across New Zealand, and how a three-phase, four-wire system delivers power to homes and businesses. Now, we'll move on to the multiple earth neutral system, commonly known as the MEN system. This is the standard earthing method used in New Zealand's low-voltage supply network, and it's one of the most important safety features in our entire electrical system. Let's begin with Topic A, how the MEN system is configured. Topic A, how the MEN system is configured. In New Zealand, the MEN system is used for low-voltage supplies up to 230-400 volts. It combines the neutral conductor and the earth system so they work together to ensure fast disconnection of faults. Here's how it's arranged. The supply transformer has its neutral point earth. The neutral conductor from the transformer runs to the consumer's installation. At the main switchboard, the neutral bar is connected to an earth electrode. This is called the MEN link. So, in simple terms, the neutral is earthed at the transformer and again at each installation. This creates a network of multiple earth connections, hence the name multiple earth neutral. Topic B, why the neutral is earthed at multiple points. The neutral is earthed at many points in the supply to make the system safer and more reliable. By having several earthing points, we keep the neutral to earth voltage very low, reduce the risk of a broken neutral becoming dangerous, and ensure the voltage between any exposed metalwork and true earth never rises too high. If the neutral were only earthed at one point, a fault anywhere along the line could make the whole neutral system rise to live potential. So, multiple earthing adds redundancy and stability. Topic C, purpose of the MEN system. The main purpose of the MEN system can be summed up in 3 points. 1. Maintaining a low impedance path between the neutral and earth. This ensures that if a fault occurs, fault current can flow quickly back to the source. 2. Rapid disconnection of the supply under fault conditions. Because of the low impedance path, protective devices like fuses or circuit breakers operate instantly when a fault occurs. 3. Limiting the voltage rise to earth. The MEN system ensures the voltage of exposed metal parts never exceeds about 230 volts to earth during a fault. In short, the MEN system allows faults to clear fast and keeps touch voltages low. Topic D, importance of reliable low-resistance earth circuits. Now let's move to Topic D, reliable low-resistance earth circuits. For the MEN system to work correctly, both the protective earth conductor and the bonding conductors must have low resistance. Low resistance ensures that enough current flows during a fault to operate the protective device, usually within 0.4 seconds for socket outlet circuits. If the earth path becomes high in resistance due to loose connections, corrosion, or undersized cables, fault current may not be high enough to trip the circuit breaker. That means the exposed metal parts could remain live, creating a shock hazard. So, always make sure earth and bonding connections are clean, tight, and continuous. Topic E, dangers of high-resistance earth or bonding connections. If there's a high resistance in the earth or bonding conductors, serious problems can occur. During a fault, less current flows back to the supply, so protective devices might not operate at all. The result can be dangerous touch voltages on appliance frames or switchboard panels. For example, a loose earth connection on a washing machine could make the metal body live at 230 volts, but the breaker wouldn't trip because the fault current is too small. That's why regular inspection and testing of earth continuity is essential for all installations. Topic F, implications of a missing MEN link. Now, Topic F, the effects of a missing MEN link. The MEN link connects the neutral bar to the earth bar at the main switchboard. If it's missing, broken, or loose, the system can become extremely dangerous. Here's what happens. Fault current can't return properly to the source. The circuit's voltage to earth readings become unstable. Metal parts of appliances or switchboards can become live because the neutral is no longer at earth potential. With no main link, earth fault loop impedance increases, which delays or prevents the circuit breaker from tripping. Always check the main link during testing, it's small but vital for safety. Topic G. Distribution type systems. Finally, let's look at Topic G. Distribution type systems. Sometimes, alternative supply systems like generators or UPS units are connected downstream of a main installation. When this happens, we must ensure the neutral and earth relationship stays correct. A generator connected downstream must have its own neutral earth bond or follow the existing main arrangement, never both, or it will cause circulating currents and unsafe voltages. In short, when connecting alternative supplies, always check how the main link and neutral are managed. Summary. Let's summarize Topic 8.10, Multiple Earth Neutral System. We covered how the main system is configured, why the neutral is earthed at multiple points, the main purposes of the main system, the need for reliable low-resistance earth paths, the danger of high resistance or missing main links, and how distribution systems must be properly connected downstream. The key takeaway is the main system keeps touch voltages low, allows quick disconnection of faults, and forms the backbone of safe electrical systems in New Zealand. That concludes Topic 8.10, Multiple Earth Neutral System. In our next lesson, we'll move on to Topic 8.11, Protection, where we'll look more closely at fuses, circuit breakers, and overload devices that protect circuits and equipment from excess current.